Hi everyone! In the previous video, we have discussed the Newton method in a heuristic way. We have given the iteration formula, explained its geometric interpretation, applied it to some examples, from which we have observed numerical evidence of the quadratic convergence. In this video, we will continue our discussion by showing that under some standard assumptions, the Newton method will converge at least quadratically. To start with, let us first look at the rigorous statement on the convergence of Newton's method. Let f be a one-dimensional real-valued function, and let x star be its root. Now we will put three extra assumptions. To remember them, you only need to remember three words, which are regularity, simplicity, and vicinity. Regularity means that a function f is regular in the sense that it is at least of class C2, meaning that f, the derivative of f, the second derivative of f, all exist and are continuous. Simplicity means that x star is a simple root of f, meaning that the derivative of f evaluated at x star should not vanish. Finally, the vicinity means that there exists some positive real number delta, which might be fairly small, such that if we start our iteration from the initial point x0, whose distance with x star is less than or equal to delta, then the iteration under the Newton algorithm will converge to x star at least quadratically. Now let us start our proof. We know that f is of class C2, hence f prime is a continuous function. Recall that the absolute value is also a continuous function, and the composition of continuous functions is again continuous. From there, we see that by taking a very small delta naught, we can make sure the minimum of the absolute value of f prime x is greater than 0 in this small neighborhood. Now let us consider a number c, which is defined by the maximum of the absolute value of f double prime over this interval divided by the minimum of the absolute value of the first order derivative of f in the same interval. Note that this is well defined as f prime, f double prime are all continuous functions, and continuous functions achieve maximum and minimum on closed intervals. Moreover, c is a real number. This is because by our previous discussion, the denominator is not going to vanish. Now, let us proceed to our error estimate. To this end, let us compute what is xn plus 1 minus x star. Since we're using Newton iteration, this is equal to xn minus fxn over f prime xn minus x star. After some algebraic manipulation, this becomes negative fxn plus f prime xn times x star minus xn divided by f prime xn. If we consider the Taylor theorem applied to fx star centered at xn, we have fx star is equal to fxn plus f prime xn times x star minus xn plus f double prime evaluated at some cn over 2 factorial times x star minus xn squared. The last term is just the Lagrange remainder. However, notice that fx star vanishes because x star is a root. Thus, plugging in this formula into our computation, we obtain that the left-hand side is equal to f double prime cn times x star minus xn squared over twice f prime xn. Now let us pick out delta to be the minimum of delta naught and 1 over c plus 1, where delta naught and c are chosen in the previous step. Since both candidates are positive, at their minimum, delta is also positive. Now, what if the absolute value of xn minus x star is less than or equal to delta? Well, in that case, let us take the absolute value on both hand sides of the previous equality. The left-hand side becomes the absolute value of xn plus 1 minus x star, while the right-hand side becomes f double prime cn absolute value times xn minus x star absolute value squared, divided by twice the absolute value of f prime xn. Now, notice that delta is less than or equal to delta naught. Hence, this ratio is dominated by the constant c achieved in the previous step. It follows that the right-hand side is less than or equal to 1 over 2 times c times xn minus x star absolute value square, which is in turn less than or equal to 1 over 2 times c times delta times xn minus x star absolute value. Now recall that delta is also less than or equal to 1 over c plus 1. Hence, c times delta is less than or equal to c over c plus 1, which is less than 1. From there, we finally achieved that the right-hand side is less than 1 over 2 times xn minus x star absolute value. What does this mean? This means that this delta neighborhood is attracting, in the sense that if xn is in this neighborhood, then after an iteration, the distance between xn plus 1 and x star will be at most half of the distance between xn and x star. In particular, if our initial value x0 is already in this delta neighborhood, we see that under the iteration, the distance between xn and x star will decay geometrically. This proves the convergence. Now, once the convergence is achieved, we can go one step further to show it is actually convergent quadratically at least. To see this, simply notice that since xn is converging to x star, and Cn is between xn and x star, we see the sequence Cn will also converge to x star. Now, by tending n to infinity, the absolute value of xn plus 1 minus x star over the absolute value of xn minus x star square converges to absolute value of f double prime x star over absolute value of f prime x star, where again we have used the facts that f double prime and f prime are both continuous functions. And from there, we see that the convergence will be at least quadratic. Alright, now we have proved this fundamental theorem concerning the quadratic convergence of the Newton method. Keep in mind that the violation of any of these three conditions can have negative impact on the performance of the Newton method, which will be the topic of the next few sections.